This is page 555, and we're going to talk about generalizing the tangent ratio. Let's begin by highlighting on our two triangles the opposite, adjacent, and hypotenuse sides, as well as identifying where the reference angle is. So since x degrees is labeled there, this is going to be our reference angle. Signified this time, we're going to start using the notation of an O with a line in the middle. That's going to be called theta. It's a Greek letter. There's other letters besides the ones we use when we count with the alphabet. We ran out of letters, and so we're going to introduce Greek letters to fill that void. There's also, in the other triangle, the same x degrees, so they get the same characterization of theta. Now I've got green for highlighting the hypotenuse, as we've been doing. And both of these triangles have a green hypotenuse side. From theta, we next identify the opposite side. So highlighting in yellow for opposite. And then last of all, the adjacent side in orange, adjacent being next to. A reminder that tangent is the ratio of opposite to adjacent. So over here, notes on the side, just to be consistent as we talk about the tangent ratio, the tangent of theta is the opposite side divided by the adjacent side. And in this case, theta is x, and then the opposite side would be L sub 1, and the adjacent side would be L sub 2. So we can use those letters, we can substitute those letters into the tangent equation, and we can write tangent of x degrees equals L sub 1 over L sub 2. A little highlight should go on there, but that's the pause for now. Now, I did start by pre-writing the answers for A, B, and C. So go ahead and maybe pause right here and pre-write. I'm going to have a gap right there where I write a number. I'm going to have a gap right there where I write a number. And then I'm going to write a sentence with you at the end. And then I hope these are the good sentence stems to start those next three sentences in part B. So pause here, write, and then resume. That should be enough time for me that you pause and resume. So let's go. When one acute angle of a triangle has a measure of x degrees, so we're referencing this triangle, what algebraic expression represents the measure of the second acute angle? You do realize, by the way, guys, that there is another acute angle up in this corner, and in this corner of both, since those triangles are similar, that they are both going to have the same measurement. But what is the way we could calculate that measurement quickly? Well, since the angles in a triangle add up to, do you remember? 180 degrees. And the box in the corner means 90 degrees. Then if you add up these angles of the triangle, they have to add up to 180. And since we don't know how big, like what expression represents this third angle, let's just leave it as a question mark for now. We would have 180 equals 90 plus x degrees plus the question mark. Now, in order to figure out the value of the question mark, we subtract. It's like solving an equation. So if you have an equation where you have 180 equals 90 plus x plus question mark, to get the question mark by itself, we subtract. So I'm going to take away 90, take away x. What you do to one side of the equation, you do to the other. So over here, subtracting 90 from 90 gives us 0. And subtracting x from x also gives us 0. It'll leave us with the question mark all by itself. So a little arrow here, question mark equals. And then on this side, we have to do some combining like terms and simplifying. So 180 and 90, they're constants. We can subtract them. 180 minus 90 is 90. And then take away x. So that subtracting x from both sides of the equation. Now, with that in mind, what we have is an actual algebraic expression for the other angle in a 90-degree, right triangle. It specifically is 90 take away x. 90 subtract x. Now, what does that mean that we can say about the two triangles? So we have these two triangles here. They are the same shape, but that means they're different in size. If you remember responding to your online homework, there was that way of discussing whether or not the triangles were similar, and similar meant same shape, different in size. Similar, they could be congruent, but likely we should be able to use our eyes to realize that this triangle is bigger than the other one. So that makes them similar, but not congruent. And if we're going to say that the triangles are similar, we have to have a shortcut that proves it. Our shortcut in this case is angle, angle. Triangle similarity. And that's a theorem. It does that we have a 90-degree angle in this right triangle. All this module, this new topic right now is based upon right triangles. So we're looking for the box as often as we can find it in our diagrams so that we know that we can start using tangent and some of the other trig shortcuts. Let's go to the last one. When the side opposite the acute angle, measuring by x, is in the smaller triangle of length L1, what algebraic expression represents the length of the side opposite the acute angle measuring x in the larger triangle? I had to wrap my head around this question for a second. If this is L1, down here in the bottom, then what expression is going to be the length of the side opposite from it? And then it reminded me of the idea of scale factor. So because of scale factor, we can write or find a multiplication number that will allow us to multiply this side to become the length of the other side triangle. So if I say our scale factor, and again, go back to topic 1 conversation, but you take the larger shape and divide it by the smaller shape, or you take the image and divide it by the pre-image, which I'm going to put right here, image over pre-image. Because of that fraction, this is going to be our scale factor. I'm going to call it an A just for, like I need a letter. I need a factor letter. So I'm going to multiply by A. I can find the length of the other triangle's long side or opposite side by multiplying L1 times A. And that'll equal the other triangle's other side, because the scale factor multiplies all sides of the triangle in the same amount. I might be getting ahead of the next page, page 556. That's the next video, but I can write that on this page right now and then pick it up in the next video as well. If A is my scale factor, I don't know what A is right now because there are no numbers. But if I did have numbers, I would do this formula down here, image divided by pre-image, and I could figure out what the scale factor was. I multiply the side here by A, and I get the long-sided of the triangle. I can do the same thing for L2, A times L2. Because if I know the side length, the second side length, and I have my scale factor of A, then I multiply L2 by A, and I get the new side length. We need some examples for sure, but right now, we're just multiplying. That's all that's been happening. Thank you for watching page 555. We're going to go ahead and end the video for this page right now. Page 556 is next, and I'll see you in the next episode.